So we're doing problem number 23. So chapter 31, problem 23. And in this problem, we have the current in a long solenoid of radius big R equals 3 centimeters. So let's go ahead and write these things down as we get them. And this current is increasing uniformly at a rate of 1.5 amperes per second. So current increasing, how would we write that? What's that variable? Di over dt, perfect. Change in current divided by change in time was 1.5 amperes per second. The solenoid has 350 turns per meter. What's that? What letter is turns per meter? N, big N or little n? Little n, which is also equal to big N divided by big L, which is 350 turns per meter. Okay, so that's how many times you've wrapped around this coil. So if we draw a picture of this, a solenoid looks like this. A whole bunch of little coils. So we're just doing 350 turns. I'm not going to draw 350 little wraps. Okay. We are asked, what is the induced electric field, a distance little r from the solenoid axis when our distance away from that axis is 2 centimeters and when our distance away from the axis is 4 centimeters. Okay. So we want to find the induced electric field.
He thinks he's funny.
She was in here for the joke.
Yeah. We stopped you. You opened the door, right?
Yeah.
Yeah. You just tried to open it. You didn't just stand there, look dejected.
Oh no, she did.
Did you waver in? Well, I'm testing to see how many people just stand at the door and look dejected, or how many people come and see the door and then just walk away. I've had that happen, and then I chase after them because I'm a sucker. Okay, so how do we do this problem? We need to find the induced electric field. Gosh, how do I find that? I can find some things that have to do with induction. Usually what I find in induction problems, I find induced EMF. So I can find the induced EMF. That has a couple different ways we can find it. It's equal to negative d phi dt. Can we see anywhere that I might want to use that? Anywhere, any variables that I know that might come in useful in d phi dt? If we can't see, we'll see later on maybe.
Can you ask the question again?
Do we see any useful variables that I was given that might help us in finding this? Anything up here look like this?
D phi equals the B times A, and then you can find
D phi
A.
is B times A.
And then you can find A from R.
Times A from R.
Because isn't it pi R squared?
Okay, yeah. We'll start working with this and start trying to find some stuff. But we also knew EMF is equal to another equation. EMF is also equal to the integral of E ds. So they're equivalent, right? I'm looking for E, so I probably want to use this equation down here because that has an E in it. E is inside of the integral, but E doesn't depend on the variable in here. So I can pull E out of the integral. And the shape that I'm integrating over, I'm doing a surface integral, is a circle. So this integral of E ds, that's equal to the circumference. The circumference of where I'm calculating the field. Okay. So, what's the circumference of a circle?
Pi R.
Yep, so this EMF is equal to E times 2 pi r. So now what I've done here is I've derived an equation. I can solve this equation for E equals the EMF over 2 times pi times little r. Where little r is my position. It'd be those two different numbers, part A and part B. So now what do I have to find? I'm looking for E. I know 2, I know pi, I know what the r's will be in part A and part B. What's the unknown variable there?
The EMF.
The squiggly E, the EMF. So I have to find EMF. And I can turn to this other equation for finding the EMF. This problem is deceptively difficult. So I have to find the EMF. EMF is going to come from negative d phi dt. To find d phi dt, I need to find the derivative with respect to time of b times a. Magnetic field times the area. So what's the magnetic field of this thing? What kind of shape is this?
Cylinder.
They tell us it's a solenoid. So I have an equation for the magnetic field of a solenoid. Where does this equation come from? Mu naught n over L times I. Where does that equation come from?
Textbook.
Textbook? I looked in chapter 31. I didn't see this equation anywhere in chapter 31.
My cheat sheet.
Chapter 30.
I didn't see it in chapter 30 either. Brandy? Yeah, this is equation 29.21. So that's a given. That's something you should know or have on your cheat sheets. This is why I suggest no cards. No cards are very, very useful. So I can find what phi is, right? Phi is B times A. So it's going to be mu naught times N over L times I times A. A is the area. What kind of shape is this?
I still think it's a cylinder.
It's a cylinder, but I'm doing the cross section. So when I'm doing the cross section, what that means is I take my cylinder and I cut a slice off of all of it. So that's just one face. What's the area of this face? Circle. Pi r squared. So I'm going to do b times pi r squared. And I'm going to give this a different r. I'm going to label that r1, r little one. Because that is all intrinsic to your solenoid. Okay. So now, this is the flux. This is B times A. Do I want just the flux? What am I looking for?
You have to put it in back in CP.
I want the EMF. I have to take the derivative of all of this. The EMF is the derivative of the flux with respect to time, so I have to take the derivative of all of this with respect to time. So that will let me find the EMF. EMF, go to d phi dt. So it's the derivative with respect to time of mu naught n over L I times pi times r1 squared. Now I have to think about the derivative of all this. We have to think about what quantities are changing with respect to time as time goes by. As time goes by, does mu naught change?
No,
No, mu naught's constant. So do I have to differentiate it? No, it's constant. It comes out front. The number of turns per length, does that change inside of this coil? They didn't tell us anything about it changing. So N over L comes out. The current, is the current changing?
Yeah.
Yeah. So there's going to be some changing current with respect to time. So I have to keep that in the derivative. Does pi change? Pi doesn't change. Does R1 change? The size of this coil? No, doesn't change. Okay, so we don't care about any of these things. So most of these variables come out. Mu naught, N over L, pi r1 squared. And then I'm left with this di dt. Now, in past problems, usually when we have a di dt, we'd have to take a derivative of an equation. Do we have to do that here? No? Why not? It's given to us in the very first part of the problem as a constant. So that's just a number. Okay, so now I have this EMF. I can use this EMF. I can plug it in way up here. Huh? So we're doing lots and lots of algebra. This is some real physics. This is what physicists do. Play with equations all day.
It's a really boring life.
It is. That's why I'm an astrophysicist. Okay, so we take this and we plug it in up top. When we plug this in, what do we get? So we have E is equal to negative mu naught n over L pi r1 squared di over dt. Then I'm going to multiply this by 1 over 2 pi r. Okay, where did that come from? 1 over 2 pi r. Just write that. So I wrote down my whole E, with all this, and then instead of just dividing that by 2 pi r, I just multiplied it by 1 over 2 pi r. So it looked a little nice. So I didn't have fractions over fractions. Yeah. Same exact thing. So that's just plugging and chugging at that point. Now what numbers can I plug in? Let's see. E is equal to negative mu naught. What's mu naught? Mu naught is 4 pi times 10 to the negative 7. What's n divided by L? Number of turns per unit length. 350. How do we know that? It was given. What's pi? Pi. What's r1 squared? So in part A, what position am I interested in? Current in a long solenoid of radius 3 centimeters. So that's how big this solenoid is. But I want to know what is the induced electric field at a distance little r from the solenoid axis when r equals 2 centimeters. Can I possibly have that thing be a radius of 3 centimeters when I'm interested in a position of 2 centimeters? No. So I have to plug in 2 centimeters. So I have 0.02. di dt. What's di dt? Yep. So I've got this solenoid. It has a total radius of 3 centimeters. But in part A, I'm not interested in what's going on at 3 centimeters. I'm interested in what's going on at 2 centimeters. So I'm interested at this position. If I'm interested at a position that's not on the edge of that cylinder, that doesn't incorporate all the outer edge, I can't plug in that outer edge. The magnetic field that I'm getting, the magnetic field I'm creating, has to be at that position. Okay. Has to be inside the cylinder, so I can't go all the way to the outer edge of the cylinder. And then I do, what do? I do 1 divided by 2 times pi times r. What's r? What's this r? For A, it's 0.02 meters. So then you plug and chug all of these numbers in, and you will get your induced electric field is 6.6 times 10 to the negative 6. di dt, yeah, plug that in here. Yep. And di dt is, what was di dt? 1.5. We've got a 1.5 in here. Multiply it all together. 6.6 times 10 to the negative 6 volts per meter. Questions on that? So it's just a plug and chug problem. And then we need to do it again for part B. Part B, a couple things are going to change. Yeah, toss the negative in there. So part B, I'm going to use the same equation. Negative mu naught n over L pi r1 squared di dt times 1 over 2 pi r. Plug and chug our variables in. What's mu naught? 4 pi times 10 to the negative 7. What's n over L?
350.
350 turns per unit length. What's di dt? 1.5. Pi is pi. What's my R1 now? What position am I at?
Yeah, it's 0.04 meters.
I'm at a position of 0.04 meters. Here's my cylinder. Here's my solenoid. My solenoid has a maximum size of 3 centimeters. The magnetic field that is created is limited by the size of that solenoid. So even though I'm at 4 centimeters, that solenoid doesn't reach out that far. Okay? So what's the radius there?
Why is it just 3? Oh, because it says radius 3. Is that why?
Yep, has to be 0.03 meters. Even though I'm calculating the electric field that's induced at 4 centimeters, this whole magnetic field that's created by the solenoid has to be dependent on the solenoid properties. So the biggest radius I can have for that solenoid is the size of the solenoid, 3 centimeters. I can get out of the edge. I can't start including pieces where I don't have any solenoid. And then I incorporate the position that I'm actually interested in when I do the 1 divided by 2 times pi times 0.04 meters. Position of interest. Make sure to square that radius. This is all negative, and E is equal to negative 7.4 times 10 to the negative 6. It's a plug and chug question. Do you have any questions on this? Hey, it recorded the whole time. No questions?
What are the units?
What are the units? What are the units of E?
C times meter squared?
Units of E are volts per meter.
Oh, okay. Good to know.
Tesla times meter squared might be correct. I'd have to work it out.
Okay.
All right, let's do another problem. Let's do problem number 29. So in problem 29, we have a rectangular loop that measures 20 centimeters by 80 centimeters that's made of heavy copper wire of radius 0.13 centimeters. Suppose you shove this loop short side first at a speed of 0.4 meters per second into a magnetic field of 5 times 10 to the negative 2 Tesla. The rectangle is face on to the magnetic field and the trailing short side remains outside the magnetic field. What induced current will flow around the loop? So let's draw a picture of what this looks like. Here's our magnetic field. We have a rectangular loop that I'm pulling. Rectangular loop has a width. The width is 80 centimeters, and it has a height. The height is 20 centimeters. I am told that the wire that this is made out of is copper. It has a radius of 0.13 centimeters. And I'm pulling this whole thing out of this field with a velocity of 0.4 meters per second. And the magnetic field that goes into the page is 5 times 10 to the negative 2 Tesla. So this is all given to us. What am I asked to find?
Induced current.
Induced current. What letter is induced current? What letter is current? I. So I need to find I that is induced inside of this. What are we used to finding for induction? We don't find induced currents. What do we have an equation for?
Induced electric field.
Induced electric field and
Magnetic field.
let me see if the chapter actually tells you. It doesn't really tell you. But the main thing that we find induction for is Faraday's law of induction. And we're finding induced EMFs. We find E. Squiggly E. Induced EMF. What is EMF? Negative d phi dt. Induced EMF is also equal to integral of E dot ds. Which one of these would we probably use? And how would I figure it out?
The top one,
Why?
because we can solve for phi, because we have magnetic field and area.
We can find phi because it's B times A. I have B. I have an area here. So I can solve that one. Can I solve the bottom one? Can I find what E is?
What is DS?
ds is the integral, basically the perimeter around your surface. So I can find that. Can I find E
yeah.
super easily?
Yeah, you can. Or not easily, but you can.
Sure, we could probably do it using either equation, but the one that we know the exact approach is the first one. That's the one we've been dominantly using in most of the homeworks, if you've done most of the homeworks. Which you should have by now, because it's the second time doing this chapter. Okay? So we need to find negative d dt of B times A. Okay. So we need to find negative d dt of B. What's the area of this? What's the area of a rectangle?
It's 80 times 20 times 10 to the negative.
Is it 80 times 20?
Yes.
But I'm pulling this thing out, so that area is changing. What's the general equation for area of a rectangle?
The length times the width.
Length times the width. Right? So we can do length. I actually did length times height. Because I think of it as a length of 80 centimeters and a height of 20 centimeters. Either way, if you want it. So I need to start taking some derivatives of these things in case things are changing. Perhaps the strangest snack to have during class. There's somebody eating pickles
And carrots.
and carrot. This is very, very, very odd. Had to come. Okay, so we have the EMF is negative derivative of B. Is the magnetic field changing? Did they give us that this is changing? No. So do I have to take the derivative of B? No, comes out in front. The length that's inside of this, is that changing? As I'm pulling this over. Right now, maybe I've got 40 centimeters. If I pull it over, how many centimeters do I have? I have maybe fewer. So is that changing? So the length is changing. I have to have a dl dt. How about h? Is the height that's inside of this changing?
No.
If I'm pulling this to the side,
The
that
stays
height
the
is
same.
still entirely in there. So the height doesn't change. So I can pull a couple things out of that derivative. I can pull out the b, I can pull out the h, but I have to keep that l in there. So I have B times H times dl dt. Well, this is a change in position. This is a change in time. What's change in position over change in time from physics 1? That's velocity. So I have an EMF that's equal to negative B times H times V. So I can calculate this EMF. EMF is negative B. B was equal to 5 times 10 to the negative 2.
Yeah.
And H, what's the height?
0.2.
0.2 meters. And what's the velocity? How fast is this thing going? 0.4 meters per second. That gives me my EMF. My EMF is also 4 times 10 to the negative 3. So I can calculate the EMF, and normally that's where we'd be done. Did this ask us to find the EMF? No, what did they ask? They asked for the current. If you have the current, if you have the voltage, you want to know the current. How are voltage and current related to each other? E equals I times R. Where does that come from? Chapter 26, whose law is that? That's Ohm's law.
Yeah.
Divide both sides by R, and I can find that the induced current is the EMF divided by the resistance. So if I had the resistance, did they give us the resistance? That'd be very nice of them. They didn't give us the resistance. But they did give us that this was a copper pipe, and I can find the resistance. Resistance is equal to rho, the resistivity of an object, times L divided by the area. So this is resistance of a wire. It depends on resistivity, which is intrinsic to the material that you're given. What material do I have here? Copper. So that's a clue that you're going to have to use something related to copper in the problem. That's a kind of key word that tells you you're going to have to use something like this. How would we get that number? How would I get what that resistivity is?
Your
Cheat sheet, you'd be given it. It's from a table. So you go to a big handbook, look up what the resistivity of copper is. It is equal to 1.7 times 10 to the negative 8. Then we need to know the length of the wire that's inside of this magnetic field. The total, not just inside of the magnetic field, just the total length of the wire. How do I find the total length of this wire? How big is this wire?
Isn't it 80 centimeters?
How big is this wire? So we are adding up all the heat, all the resistance that we're getting throughout this entire wire, this entire loop. How do I get the entire amount of wire that I would need to build this loop?
Circumference?
Circumference. What's the circumference? Can you do the circumference of a rectangle?
Don't you do 80 plus 80 plus 20 plus 20?
Well, 80 plus 80 plus 20 plus 20, that's not the circumference. What is that called? Perimeter. Do the perimeter.
Yeah.
Same concept as circumference. Just 80 centimeters plus 20 plus 80 plus 20. All the way around. That gives you the total length of that wire. So that's 0.8 plus 0.8 plus 0.2 plus 0.2. All divided by the area, the cross-sectional area of a wire. What's the cross-sectional area? What shape is a wire? Wire is a cylinder. What's the cross-sectional area of a wire? Pi r squared. Circle. Pi r squared. What's the radius of this wire?
0.013 centimeters.
Or we'll go with 0.0013 meters. This is 0.13 centimeters. Tiny, tiny little wire. So I can plug all these numbers in. Plug all these numbers in, I get my R. I get my resistance of 6.4 times 10 to the negative 3. What are the units of resistance? Ohms. Does something like this make a good comprehensive exam question?
No.
Yeah, why? Because what am I testing? Testing everything. I'm testing this chapter, I'm testing the last chapter, for finding EMFs. I'm testing areas. I'm testing velocities from Physics 1. I'm testing resistance from Chapter 24, 25 or something.
It sounds like so much fun for you.
Oh, it is. It is. I have dreams about this, yes.
Oh gosh.
How did I find the radius of the wire? They gave it to us. They tell us that the wire is, let me get the exact wording, is made of heavy copper wire of radius 0.13 centimeters. So now I can calculate what the current is by taking the EMF and divide by the resistance. 4 times 10 to the negative 3 divided by 6.4 times 10 to the negative 3, and I get my current is 0.63 amps. There's my induced current. Any questions on that one? As we frantically scribble down everything I wrote and have no clue what I actually did right. I know how physics works. I was a physics student once.
Another question.
Yes.
So for A, how did you get 5? This plus 0.003, 13.
For what?
For the,
This?
yeah.
That's the area of a circle. Pi r squared. Okay. No other questions on that one? All right. Last one you asked about was number 86. Number 86. We have a long straight wire that carries a current that increases at a steady rate di dt. So they gave us di over dt. This one has a star, so we know it's going to be hard. Part A, what is the rate of increase of the magnetic field at a radial distance r? So I basically have a wire that has a current in it, and that current is changing at a rate di over dt. They want to know what's the change in the magnetic field if I'm a distance r away from it. So if I'm, say, over here. Let's say that the current, just for argument's sake, is going up as well.
If it's going down, I'll ask it.
Good, I would wait.
Okay.
If it's going up, I'm going to add in a question here. Instead of just calculating the magnetic field change, I want to know what direction is the magnetic field going. So here, how do I figure that out? Right-hand rule. I take my thumb pointing in the direction of I point my fingers over to the right because I'm interested in what's going on the right side of the wire. I bend my fingers, they're going into the board. So the magnetic field thing that this creates is going into the board. So maybe it creates one magnetic field line going into the board initially. And then as it's increasing, what am I going to get? I'm going to get more magnetic fields going into the board. That magnetic field is going to get bigger, so maybe I get a second one that's going in. Does that make sense? Yeah? Yes, Leah.
The second right-hand rule,
This is the second. Anytime you're using your thumb to direct where the current goes, that's the second right-hand rule. Okay. Now we need to calculate what's the change in the magnetic field on this. So we have a long straight wire. We should memorize the magnetic field of a long straight wire. What is that? Mu naught I over 2 pi r. And now I want to know how this is changing if I change what I is. So I want to know what's dB dt as the current changes. Does the current changing, does this di dt existing, does that have any effect on mu naught? No. Does it have any effect on 2? No. Pi? No. The distance away that you are? No. So do any of these things change? No. Do we know what effect it has on I? What does it make I? It makes I di dt. This is really, really easy. This is ridiculously easy. Mu naught over 2 pi r times di dt. That's your part A. That's how the magnetic field changes when you change the current.
Okay, can I ask my question?
can.
If the current was going down, would this be a negative everything?
If the current is going down, then that's going to switch the directions that the magnetic fields are going.
And then
So if the current goes down, my finger goes over to the right, finger is going out of the board, so I have magnetic fields coming out of the board.
okay, so then is the answer negative?
Nope.
Okay. It just changes the direction.
Changes the direction of the magnetic field. Okay, second part of the question. The wire is now in the same plane as a rectangular loop shown in figure blah blah blah. What is the induced EMF around the loop? Assume that A is much, much less than R. That is, the width of the loop is so small, magnetic field and its rate of change are the same at all points in the loop. Blah. We'll talk about what that means. So I have this loop. The loop is a distance R. It has a width that's equal to A and a height that's equal to L. And I want to know what's the EMF that's induced in that loop. What's the equation that we've been using for EMF? Negative d phi dt. So E in the loop is equal to negative d dt of B times A. Yep. Very, very easy problem. Is the magnetic field changing inside of this loop over here? Is there a dB dt? Is the magnetic field changing? If I'm increasing the current, is the magnetic field going to increase?
Yes.
Yes. So is the magnetic field changing?
Yes.
Yes. Do we know how it's changing? It's increasing. Do we have an equation for it? Yeah. How? That was part A. dB dt. We know how the magnetic field is changing. So there's a dB dt. How about the area? The area of this that's inside of the magnetic field. Is that changing?
No.
The area of that loop changing?
No.
So there's a key thing that they told us. They told us that this width is much, much less than L, much less than the distance. So the magnetic field over this loop, they told us, doesn't change. Right? If it did have some width, then it would change, wouldn't it? If I'm close to the wire, I'd have a bigger magnetic field than if I'm far. But if I say that the width of that doesn't really matter, then I can ignore that fact. I don't have to integrate over the size of the wire. We've done that in previous problems. We don't have to worry about that. So the area can come out of this derivative. It's not changing. So my EMF is negative A times dB dt. The EMF induced around this loop is negative A. What's the area of the loop? What's the area of that particular loop? How do I find area of a rectangle?
A times L.
A times L, length times width. Little a times L, and then dB dt is mu naught over 2 pi r times di over dt. That's the second part. That was really pretty easy for a start problem. I think we should make it harder. Do you have any questions? Plug anything in? No?
No, there's nothing
No numbers given. So that's your answer. So how do I make this harder on an exam so that it can be worth 20 points?
there. You asked for the direction.
Ask for directions of things. So what direction is the induced magnetic field going to go? I had one to start, one magnetic field going into the board. I start increasing I. That means I get another magnetic field going into the board. Is induction happy about that? What does induction want? It wants to go back to 1. So what's the direction for the induced field? Out of the board. We are going to induce something going out of the board. So that's my induced field. B induced is out of the board. what direction is the current that's going to flow inside of this loop have to be so that I get magnetic field coming out of the board? Do I need it to go, so it's going to go around this loop. I could go clockwise, or I could go counterclockwise. What do you want to guess? You want to guess counterclockwise? Okay, so let's draw in some wire, some current. So counterclockwise would be, I'd be going up on this side, over, down, and over. So that's my current going counterclockwise. If I want, I could pick any place on that loop. I could pick the bottom part, left, right, or top. They'll all give me the same thing. What side do you want to do? Bottom, top, left, or right?
Bottom.
Bottom. If I go with the bottom, I take my thumb, put it in the direction that the current's going. I want to know what the magnetic field induced direction would go due to that current if I was above that bottom wire. So I point my fingers up. I bend my fingers, they're coming out of the board. Is that what I wanted?
Yeah.
Yes. So the induced current is going counterclockwise. By adding those two little pieces, I just made this problem worth 20 points. Instead of the probably 2 points that it should be worth for plugging and chugging. Any questions?
How did you find B induced?
So I found B induced because the current is increasing. They told us that. If the current's increasing, that means the magnetic field is increasing. I'm getting more magnetic fields going into the board. I'm not happy about that. I want to go back to what I had before.
That's right.
So I cancel it out.
Okay.
Yeah? Más preguntas? No más preguntas? Todas estás bien? We're all ready for second spring break?
Yes.
You're not more ready than we are, professors. I know.